Lighthouse Scientific Education presents a lecture in the Molecules and Compounds series. The topic, Basic Dot Structures. This is the first of two dot structure lectures. The Advanced Dot Structure lecture is only for students who are expected to build these structures by starting with a total count of valence electrons. For most students, this lecture provides a sufficient understanding of the subject. Material in this lecture relies on an understanding of the previous lectures, covalent bonding, and valence electrons, octet rule, and the dot structure. Our lecture begins with a review of the roles that valence electrons and the octet rule have in covalent bonding. This will provide the base for building molecular dot structures. This review is summarized in a table giving the number of bonds formed by common atoms. Then it's on to the rules for determining a basic dot structure. We will build 6 dot structures in this lecture that cover the basic features found in dot structures. The first structure is methane, CH4. It is a basic covalent compound. Followed by water, which is a polar covalent compound. Double and triple bonded compounds are explored with O2, N2, and CO2. The topic of resonance is first explored with the compound sulfur dioxide. And we round off our coverage with NH4+ and CO3- 2 to demonstrate how to build dot structures with polyatomic ions. CO3- 2, or carbonate, also serves as a demonstration of resonance. Since the covalent bond is the sharing of valence electrons, it's worth our time to revisit the electron dot diagram of atoms. If you feel that you have a good grasp of the valence electron dot diagrams of atoms, move on to the topic octet rule, or number of bonds formed. On the other hand, if at the end of our review of electron dot diagrams for atoms, you are still unsure of how they are constructed, go back to the valence electrons, octet rule, and dot structure lecture for a more thorough description. Listed here are the first 18 elements by atomic number. Added is a column that gives the number of valence electrons for each atom. Every dot diagram starts with the symbol of the element. We will use a generic element symbol E for demonstration purposes. We will say that it can hold up to 8 valence electrons. Around the symbol are 4 equal energy orbitals placed 1 per side. Temporarily, we will use boxes to designate the orbitals. Hund's rule limits the number of electrons that these orbitals or boxes hold to no more than 2. We can generate the Hund rule on this diagram by dividing each box in half. There are now 8 half boxes. Each half box can hold an electron. We will call the filling of the 2 half boxes of the orbital as having paired electrons. Dot diagrams are constructed by adding the valence electrons as dots to the boxes, but we do so in a particular pattern. Starting at the top box and moving clockwise around the symbol, dots are added 1 per orbital. There is no pairing of electrons yet. Each orbital gets 1 electron before neighboring half boxes are both filled. After the first 4 valence electrons have been added, assuming that the element has more than 4, the pairing of dots begins. Use the same pattern of starting at the top box and moving around clockwise. Oh, and we don't really use the boxes. We will move through this table to highlight the process of assigning the correct orientation of dots around the element symbol, and we will only cover elements that make covalent bonds. Starting with column 1 or 1A elements. The only element in this column we need to concern ourselves with is hydrogen. It has 1 valence electron. By convention, a single dot is added to the top of the element symbol. We now skip over to column 3A or column 13 elements, boron and aluminum. Their 3 valence electrons go in a clockwise manner around the symbol. starting with one dot on the top, then one on the right side, and finally one on the bottom of the symbol. Carbon and silicon are column 4A or column 14 elements, and their 4 valence electrons are assigned 1 to a side. The column 5A or column 15 elements, nitrogen and phosphorus, have 5 valence electrons. The first 4 of their 5 valence electrons are assigned in the same manner as that for carbon and silicon. That 5th electron is paired at the top of the symbol. Pairing also occurs with column 6A or 16 elements. We see that oxygen and sulfur have 6 valence electrons. The first 4 valence electrons go in the normal pattern of 1 per side, and the 5th and the 6th valence electrons pair. The halogens, fluorine and chlorine, belong to column 7A or 17. The first 4 of their 7 valence electrons are added in the normal pattern, with valence electrons 5, 6, and 7 pairing. And finally, we have column 8A or 18, the noble gases neon and argon. The noble gases neon and argon have full sets of valence electrons. The other noble gas, helium, also has a full set of valence electrons. But since it only has a 1s orbital, its full set is 2 valence electrons, which are paired at the top of the helium symbol. Only hydrogen and helium do this single orbital on the top thing. A final point needs to be made about the way we arrange the dots around the symbol. That dots are added to each orbital before pairing will always hold, but where we actually add that first dot is a matter of convention. The top orbital is just the agreed upon starting orbital. Since there really isn't a top or bottom to an atom, the pattern of adding dots starting at the top is not a physical reality. We are not limited to where we start the pattern. Dot diagrams do not have fixed orientations. Take the dot diagram of nitrogen. Specifically, consider the pairing of that 5th electron. When we start the pattern of assigning the dots using the orbital on the top of the symbol, we get this preferred orientation. However, if we start the pattern on the right side, we have the pairing with this orientation. Starting on the bottom gives this pairing, and starting on the left side gives this pairing. All of these versions of the dot diagram of nitrogen are equivalent. They are the same thing. This may not seem very significant, but when we start building dot structures, we will be choosing the most convenient of such orientations. And while it's worthwhile pointing out that we are free to change orientations, remember that in doing so, we are not altering the dot diagram. The other important feature in explaining the building of a dot structure is the octet rule. It says atoms with 8 electrons in their outer shell are the most stable. We'll limit our discussion of atoms with valence electrons in their s and p orbitals. Remember that this 8 comes from filling the s orbital, 2 electrons, and the p orbitals, 3 times 2, for 6 electrons. 2 plus 6 is 8. A more detailed explanation of the octet rule is given in the valence electrons octet rule and dot structure lecture. The octet rule mostly applies to elements in the second and third row. It doesn't specifically hold for row 1 elements. A duet or 2 rule can be applied for row 1 elements. There is a shell pattern of 2, 8, 8 that represents how many electrons are required to fill the first 3 energy levels. Again, limiting ourselves to s and p orbitals. That does bring up a point, however. The only elements that have a full octet or duet are the noble gases. What about the other elements? How do non-noble gas elements get a full octet? There are 2 ways. 1, they form ions. That is, they gain or lose electrons. Or 2, they form bonds. They share electrons. How does sharing electrons get an element a full octet? In a covalent bond, an atom counts both shared electrons towards fulfilling the octet rule. That means for each covalent bond an atom enters into, it gets to count an extra electron toward fulfilling the octet rule. So when counting for the octet rule, count the starting number of valence electrons of the atom and add the number of bonds that that atom enters into. This is how we should think of covalent bonding. It gets atoms a full outer shell, and that means they are more stable. In the covalent bonding lecture, we brought up this table that looked at common atoms involved in covalent bonding as a function of the number of valence electrons that they have. We used that number to determine how many bonds an atom needs to make in order to fulfill the octet or duet rule. We also noted the number of single unpaired valence electrons in an atom dot diagram because these are the only electrons that an atom can share when making a covalent bond. It tells us how many bonds the atom can make. For hydrogen, it has one unpaired electron. It can form one covalent bond. When considering the octet or duet rule, count the starting number of valence electrons and the number of bonds. 1 plus 1 is 2, a duet. Carbon has 4 valence electrons, and they are all unpaired. It can form 4 covalent bonds. 4 valence electrons plus 4 bonds is a count of 8, a full octet. Nitrogen has 5 valence electrons, and 3 are unpaired. It can form 3 covalent bonds. 5 valence electrons plus 3 bonds is a count of 8, a full octet. Oxygen has 6 valence electrons, and 2 are unpaired. It can form 2 covalent bonds. Adding its 6 valence electrons to the 2 bonds gives a count of 8. Finally, fluorine. It can form 1 bond. Since it has 7 valence electrons, it only needs 1 bond to get a count of 8. We use the dot diagram of an atom as a guide to how many covalent bonds can be formed and which of the valence electrons are going to form them. A little terminology first. A pair of dots between 2 atoms is a single bond. 2 pairs is a double bond. And lone pair electrons are valence electrons that do not participate in bonding. They can be turned into bonding pairs, but that is a topic for later in the lecture. There are a number of ways to construct a dot structure of a molecule. Here's one of the more straightforward ways. Start with a molecular formula. From there, get the dot diagram for each atom in the molecule. If there are 2 hydrogens, get 2 hydrogen dot diagrams. A quick side note, if the molecular formula is a polyatomic ion and it is a positive ion, take electrons from the central atom. If it is a negative ion, add electrons to the outer atoms. More on this when we address polyatomic ions. Back to the main steps. Write a skeleton molecule with a central atom in the middle. The central atom is usually the atom with the lowest electronegativity. The skeleton usually follows the pattern of the dot diagram of the central atom, paying special attention to where the unpaired electrons are. It should be noted that since hydrogen can only form 1 bond, it can never be a central atom. From the skeleton, draw the dot structure by pushing the outer atoms into the central atom so that single dots can pair. Remember, covalent bonds are the sharing of electrons, so there needs to be orbital overlap of the 2 atoms involved. There may be additional pushing needed if there are still single valence electrons. They will usually be pushed into bonding positions and yield a double or triple bond. Once the structure has been assembled, it's time to double check that atoms involved in bonding fulfill the octet rule. Finally, look for resonance. Resonance is an advanced topic, and while it will be addressed in detail later in the lecture, it may be one of those topics that students do not need to have a deep understanding of. The nice thing about resonance is that we only have to consider it if the molecule of interest has a multiple bond, a double or a triple bond, and then only if there's a choice of atoms in which to make that multiple bond. Most compounds will not meet these criteria. Following these rules should lead to many, if not most, molecular dot structures. Our first basic dot structure has straightforward covalent bonds. That is, atoms share one or more valence electrons more or less equally. Methane, or CH4, will be our molecule. From this molecular formula, we need to get the dot diagrams for 1 carbon and 4 hydrogens. These 5 atoms need to be oriented in a basic skeleton that outlines what the basic dot structure will look like. The first step in this process is to decide which of the atoms is the central atom. Noting that hydrogen atoms can only form one bond and therefore cannot be a central atom, the choice falls to carbon. But what is a good orientation of the hydrogens around the carbon? A rule of thumb is to look for single, unpaired valence electrons, since covalent bonding is the sharing of such electrons. All carbon's valence electrons are unpaired, so putting a hydrogen near but not touching each unpaired electron is a good starting arrangement. From here, we push the outer atoms into the central atom and pair valence electrons. Starting with the hydrogen on the left, push it into a bonding position with the carbon. As mentioned earlier, the orientation of the dot above the hydrogen is only a convention. We can treat that dot as if it was in any one of the 4 orbitals around the hydrogen symbol. The same pushing is done with the hydrogen on the bottom, to the right, and above the carbon. Each hydrogen brings in 1 electron to the bond, and the carbon brings 1 electron to each bond. The structure appears to be complete, and it's time to verify that the atoms have fulfilled the octet rule. Well, each of the hydrogens has the same orientation of valence electrons around it. So if we verify that 1 hydrogen fulfills the octet rule, or in hydrogen's case, the duet rule, then all the hydrogens can be assumed to fulfill that rule. Using the hydrogen on the top, we see that since it gets to count both electrons in the covalent bond, it has 2 electrons, and therefore fulfills the duet rule. Importantly, carbon also gets to count those 2 electrons, as well as the other 6 valence electrons involved in the covalent bonds. Carbon has 8 valence electrons around it, and therefore fulfills the octet rule. Our last step involves looking for resonance in the structure. We need only to consider resonance with molecules that have a multiple bond, that is a double or triple bond, which methane does not have. It has 4 single bonds. The structure is complete. More commonly, though, the structure generated from this process are represented with lines in place of paired valence electrons. Both styles show the arrangement of covalent bonds around the carbon. It is really a matter of preference. Our next structure will be one that contains polar covalent bonds, and as we remember, the electrons in that bond are not shared equally. However, that does not alter how we construct the dot structure. We begin with the molecular formula, and this time it's our old friend water, H2O. We need to get the dot diagrams of 2 hydrogens and 1 oxygen. Drawing a skeleton will be based on the dot diagrams of the central atom. And as we saw with methane, hydrogen cannot be a central atom. That leaves oxygen as the central atom. Now for the orientation of the skeleton. Again, we will use the location of single unpaired electrons as our skeletal template. Place hydrogens in the general vicinity of oxygen's unpaired electrons. One side note to emphasize a point we've already covered. Hydrogen's single electron is by convention put at the top of the symbol. If putting the dot on the side makes generating the skeleton or pushing the atoms together easier, then do so. The hydrogen on the left side is pushed into the central atom, pairing electrons. The hydrogen underneath is also pushed into the oxygen, pairing electrons. No need to concern ourselves with whether or not these electrons are shared equally. That is not the role of the dot structure. To the octet rule. Each hydrogen forms one bond. Hydrogen can count both electrons in its bond. Both hydrogens have fulfilled the duet rule. Oxygen gets to count these electrons too, as well as the 4 lone pair valence electrons. It too has fulfilled the octet rule. Do we need to look for resonance? We consider resonance only for structures that have multiple bonds. Water only has single bonds. Our structure is complete. Other presentations of the structure have the single bonds as lines. And sometimes those lone pair electrons are also represented with lines. Lines represent pairs of electrons. Our next major group of structures involve multiple bonds. Multiple bonds are covalent bonds, but an atom shares more than one of its valence electrons with another atom. Our example is molecular oxygen with a molecular formula of O2. For dot diagrams, we bring up 2 oxygen atoms. For ease of viewing and pushing, we will turn the orientation of valence electrons. The oxygen on the left. Same arrangement, different orientation. There will not be much confusion in selecting a skeleton for this molecule. There are only 2 atoms, and they will have to be next to each other in order to form a covalent bond. Since they are the same atom, there will not be a central atom. One oxygen is not more or less electronegative than the other oxygen. But to keep constant with the rules, we can consider the oxygen on the right as the central atom. A common question that comes up at the skeleton step is whether or not it is okay to orient the atoms from top to bottom rather than side to side. While this orientation will yield the same arrangement of valence electrons around the 2 oxygen atoms, it is not the generally accepted way. It's a matter of convention. Usually the orientation of the atoms is left to right, if possible, and top to bottom, if needed. Kind of the way we read and write. So, back to left and right, and onto pushing dot diagrams together. We will push them together such that single valence electrons pair up. Does it matter which of the single unpaired electrons we choose to push into bonds? No, it doesn't. We will end up with the same structure regardless of which electrons we choose. Bring the oxygens together and form a single bond. The structure may look like it's complete, but it has a problem. Each oxygen has a single unpaired electron. Additionally, if we were to check to see if the oxygens fulfill the octet rule, we would find that each oxygen has 7 valence electrons. For almost all structures at this level of chemistry, we will be pairing all valence electrons. In other words, we're not done pushing electrons. Since this is our first structure in which we had single unpaired electrons, we should review our options. We can move valence electrons, but only if we move them into a bonding pair or move them into a lone pair. Moving them into a bonding pair will let both atoms count them towards the fulfillment of the octet rule. What we're going to do is move this unpaired electron into a bonding position between the oxygens, and this unpaired electron into a bonding position between the oxygens. We have formed a double bond. There are 2 covalent bonds between the oxygens, and importantly, no single valence electrons. They are all paired. As for the octet rule, since both oxygens have the same arrangement of electrons around them, if we verify that one oxygen fulfills the octet rule, it implies that the other one does too. Consider our central atom. There are 4 lone pair valence electrons and 4 more valence electrons as bonding electrons. The central atom gets to count all of the shared electrons, giving it a total of 8 valence electrons in its outer shell. We should check for resonance here because the molecule does have a multiple bond. It has a double bond. The reason that molecular oxygen does not have resonance is because resonance requires there to be a choice of atoms that make that double bond. There is no choice. It has to be between those 2 oxygens. We will come across structures that have multiple bonds and have the choice of where that multiple bond is placed. This is where resonance will be covered. The dot structure can also be represented with 2 lines replacing the 2 sets of shared electrons in the double bond. Additionally, the lone pair electrons can be displayed as dots or lines as shown here. This is a double bond. What would a triple bond look like? For that, we will use nitrogen in the form of N2. A look at the dot diagrams of the nitrogen shows it to have 3 single unpaired valence electrons. That's a pretty good indicator that nitrogen is going to make 3 covalent bonds. As with the 2 atoms in molecular oxygen, the 2 atoms in N2 are going to have to be next to each other. We can consider the nitrogen on the right to be the central atom, but in reality nitrogens are equal and we could just as easily skip this. As for orientation of the dot diagram, notice how the lone pair valence electrons are on the side of the element symbol away from where the bonding will occur. Placing the lone pair electrons away from the bonding site and placing unpaired electrons close to the bonding site is always a smart step. On to the push. So, which unpaired electrons should we first pair up? Any of the 3 electrons on nitrogen can serve as its contribution to a single bond. How about using the ones that are facing each other? Bring the nitrogens together such that the single valence electrons pair up and form a single bond. We have the same problem we had with molecular oxygen when the atoms were first brought together. That is, they have unpaired valence electrons. And we need to pair up all valence electrons. As we did with O2, we will move the electrons into bonding positions. There's more pushing to do. We can take this unpaired electron and move it into a bonding position between the nitrogens. The other nitrogen, we can take one of its unpaired electrons and move it into a bonding position between the nitrogens. These 2 electrons pair up to form a second covalent bond. But we're not done yet. This unpaired electron is also moved into a bonding position, as is this unpaired electron, which completes the 3rd covalent bond. The 2 nitrogens share 6 valence electrons in 3 covalent bonds. Do they fulfill the octet rule? Using nitrogen on the right, we see that it has 2 electrons as lone pair, and 2, 4, 6 valence electrons as shared bonding electrons. Yes, it fulfills the octet rule. The other nitrogen has a similar arrangement of dots and will also fulfill the octet rule. Does it have resonance? N2 has a multiple bond. However, there is no choice of how to arrange the triple bond, therefore there is no resonance. The structure is complete. The N2 structure can be represented with 3 lines as 3 covalent bonds. Lone pair electrons can also be included as lines. Another molecule with multiple bonds is carbon dioxide, which has a molecular formula of CO2. There are 3 atoms in the compound, and we will need 3 dot diagrams, 1 for carbon and 2 for oxygen. getting a skeleton won't be as easy as the previous two examples. The first thing that needs to be decided is which of the atoms is the central atom. That will be the one with the lowest electronegativity. Consulting a periodic table containing electronegativity values shows us that carbon has a value of 2.5, while oxygen has a larger value of 3.5. Carbon is therefore the central atom. A look at carbon's dot diagram shows it to have 4 orbitals containing a single electron. Carbon can make 4 covalent bonds. But we do not have 4 atoms to bond with carbon. We only have 2 oxygens. We will need to make a choice as to which 2 of carbon's 4 valence electrons we will start with to form covalent bonds. Let's go with left to right, only because it is the most common orientation. And we have our skeleton. To make the pushing easier, we can move the pair of electrons on the oxygen to the left from this side to this side. No real change has occurred. It is only a reorientation of the dot pattern. Now to the push. The oxygen to the left is brought to the carbon and the valence electrons form a bonding pair. Same thing with the oxygen to the right. Is our structure complete? No, there are unpaired electrons, and we need to pair all valence electrons. There are 2 on carbon and 1 each on the oxygens. We know our options, and we know that carbon makes 4 bonds. We will be moving electrons into bonding positions. Before we start moving electrons, let's give ourselves a little room. Slide the oxygens over a bit. That's better. We can begin moving unpaired electrons into bonding positions with this unpaired electron on the carbon. Do we have to start here? No. All of the unpaired electrons will need to be paired up, so any dot will do. Put the first dot in its place. And we might as well move the unpaired electron on the oxygen adjacent to the dot we just moved. That pairs up those 2 electrons and forms a double bond. That leaves the other unpaired electron from carbon to be moved into a bonding position between the oxygen. The unpaired electron from that oxygen is then moved into a bonding position such that it pairs up and a second double bond is formed. Do the atoms in this dot structure fulfill the Octet Rule? Looking at carbon, we see that it has 4 valence electrons from one set of double bonds and 4 more from the other double bond. Yes, it has 8 valence electrons around it. A check of the oxygen on the right shows it to have 4 valence electrons in its 2 lone pairs and 4 in the double bond. That's 8 valence electrons. The other oxygen has the same ratio of lone pair and binding pair electrons, so it also has an octet. Is there resonance? CO2 does have multiple bonds, but there is no choice as to where those bonds can be placed. They have to be exactly where they are. So, no resonance, and we have our structure. Other representations include showing the double bond has 2 lines, and if we want to see all the valence electrons, we can add dots or lines to the oxygens. It's time to build a structure that has resonance. Resonance is an important feature of dot structures, but it is an advanced topic that not all students will need to be proficient at. The student needs to be aware of what is expected of them. The molecule we will use in our demonstration is sulfur dioxide, SO2. We bring up the dot diagrams of 1 sulfur and 2 oxygens. There are some more involved steps in building the structure. So, to help keep a bit more order, 2 valence electrons on top of the sulfur symbol have been given the form of stars, and 1 valence electron on each oxygen has been given the shape of a diamond. Dots, stars, diamonds, they're all just cartoon representations of valence electrons, but the different shapes will be helpful in our demonstration. In constructing a skeleton, we need to first find a central atom. That's the one with the lowest electronegativity. sulfur has a value of 2.6 and oxygen of 3.5. Sulfur has the lower value and is the central atom. Looking at the dot diagram of sulfur, we see that it has two unpaired valence electrons, which means it can make two covalent bonds. Oh, and look, we have two oxygens that it can bind to. Placing the oxygens near the unpaired electrons on sulfur, and arranging the orientation of the dot diagrams of the oxygens, such that the unpaired electrons, in the form of dots, are pointing at the sulfur, gives us our skeleton. For the moment, the diamond dots on the oxygen will not be pushed into bonds. And onto the push. Take the oxygen to the left and bring it in to the unpaired valence electron on sulfur. A bonding pair is formed. Same type approach with the oxygen from below. Another single bond. Are we done? Not yet. We still have a couple of unpaired electrons. Looking at our options, we find that the first option is to move the unpaired electrons into a bonding position. Okay, let's start with the lower oxygen and move the green diamond valence electron. It can be moved into a bonding position between itself and the sulfur. Why not form a bond between the two oxygens? Well, there are such molecules that link their atoms together, and they're called ring structures. But they definitely have advanced dot structures and should not be attempted without guidance. As such, we should avoid making rings. Oxygen's electron will go right here. Now, that blue diamond electron on the other oxygen, it should join the green diamond and form a covalent bond, a double bond. There are no more unpaired electrons, and we should verify whether or not our atoms fulfill the octet rule. Sulfur has 4 valence electrons in lone pairs and 6 valence electrons in the form of a single and double bond. That's 10 valence electrons. That just might be too many. The oxygen to the left has 4 valence electrons in lone pairs and 2 in the single bond. It has 6 valence electrons. That's too few. The oxygen below has 4 valence electrons in lone pairs and 4 more in the double bond. That's 8 valence electrons, and if I may say, is just right. So no, we are not checking off the octet rule. We are going to have to go back and do a little more pushing. But with which electrons? Well, where are the problems? Sulfur has too many, and the oxygen on the left has too few. Whatever we do, it will involve moving pairs of electrons. What if we move the star electrons on the sulfur to the oxygen with just 6 valence electrons? Should we move them into a bonding position? If we do that, sulfur will still get to count them and will still have 10 valence electrons. But if we move them into a lone pair position on the oxygen, sulfur will no longer get to count them. Only the oxygen will. Moving the pair over to oxygen changes the number of valence electrons on the atoms involved in the transfer. Another check for fulfillment of the octet rule. We now find that sulfur has 2 electrons from its lone pair, 2 more from a single bond, and 4 more from the double bond. Sulfur has an octet of valence electrons. And the oxygen with the star electrons? It has 6 electrons in 3 lone pairs, and 2 more in the single bond. It now has 8 valence electrons and a full octet. The other oxygen is unchanged in the exchange, so it still has an octet. Our structure looks like it's ready for the last step. Check for resonance. Is there a multiple bond? Yes, there is a double bond. Is there a choice as to where that double bond is? We put the double bond between this oxygen and the sulfur, but we could have just as easily put the double bond between this oxygen and the sulfur. Since there is a choice of where the double bond can go, SO2 will be said to have resonance structures. One molecule of SO2 could be found in a different dot structure than another molecule of SO2. Some types of molecules readily convert between the different arrangements available to them, but the term resonance only implies that there are additional arrangements that satisfy the rules. That second arrangement can be found by returning to the step where we just pushed the dot diagrams together. Stars and diamonds are still on their original atom. Moving the unpaired diamond electrons into a bonding position between the other oxygen and sulfur generates a new location for the double bond. Handling the excess of electrons on sulfur by moving the star-shaped electrons onto this oxygen, the one that only has a single bond, produces the second dot structure, a resonance structure. Checking on the Octet Rule shows that sulfur to have 8 valence electrons, as does the oxygen, making a double bond, as does the oxygen, making a single bond. There are a couple additional elements that need to be considered when displaying the dot diagram of a molecule with resonance structures. The first is that all structures need to be displayed. Both of SO2 structures are displayed in a proper SO2 dot diagram. The second is that a two-headed arrow is placed between the structures that are related by resonance. One last point. While these structures are adequate representations of the dot structure of sulfur dioxide, the more common representation is with the 3 atoms in a line. Same with the second representation. Other representations include showing the bonds as lines, and if the dot structure is to be used in generating geometric shapes of a molecule, the lone pair on the central atom will need to be included. The lone pair can be displayed as dots or as lines, as well as the lone pair on the oxygens. On to the dot structure of polyatomic ions. Dot structures for polyatomic ions are constructed the same way as neutral molecules, except one or more electrons are added or subtracted based on the charge. We will look at both a positive and a negative polyatomic ion. Starting with the positively charged ammonium ion, NH4+. Begin by bringing up the dot diagrams of 1 nitrogen and 4 hydrogens. As we've seen with previous structures, hydrogen cannot be a central atom, leaving the nitrogen as the central atom. One of the first things we may notice is that the nitrogen has 3 single unpaired electrons. That means nitrogen can make 3 bonds. There are, however, 4 hydrogen atoms that are going to be combined to that nitrogen in order to make the ammonium ion. What gives? Remember that there is a positive charge on the ammonium ion. It has 1 less electron than protons. One of the valence electrons has to go. Polyatomic ions require a bit of modification to the dot diagram step. For positive polyatomic ions, we will be removing an electron from the central atom before we construct the skeleton. Removing one of the paired electrons produces a positive charge, as well as creating an orbital with an unpaired electron that can form a covalent bond. Nitrogen now has 4 places to form 4 bonds. These will also serve as an orientation for the skeleton. The hydrogens are aligned near the 4 unpaired electrons on nitrogen. And that means it's time to push the outer atoms into the central atom to form covalent bonds. This structure seems complete, but we should verify that the atoms follow the Octet Rule. Each hydrogen makes 1 covalent bond and counts both of the electrons, thereby satisfying the duet rule. Nitrogen also gets to count the electrons in a covalent bond, giving it a total of 8 valence electrons, thereby satisfying the Octet Rule. And resonance? Well, there aren't any multiple bonds, so no, there isn't any. What's left is proper presentation. That begins with the addition of parentheses around the structure and the transfer of the positive sign to the outside of the parentheses up in the right corner. This is more in line with the molecular formula, which puts the charge on the ion after the atom types and numbers. The parentheses indicates that the positive charge belongs to the whole ion. If there is no charge, there's no need for these parentheses. The structure can also be represented with lines and single bonds. Our final structure is a negatively charged polyatomic ion, which has resonance. Our ion is carbonate with the molecular formula CO3 and having a -2 charge. The dot diagrams to be used are 3 oxygens and 1 carbon. Before we move on to the skeleton, we should take note of that -2 charge. That means there are 2 more electrons than protons. With the positively charged polyatomic ion, we removed an electron from the central atom. With a negatively 2 charged polyatomic ion, we are going to add 2 electrons to the outer atoms. Let's just put them up here for a moment. We'll get back to them. Okay, which atom is the central atom? That question belongs to the skeleton step. A quick referral to the periodic table of elements shows that carbon has a smaller electronegativity, 2.5 compared to 3.5. Carbon is therefore the central atom. That means the oxygens are the outer atoms. A look at a dot diagram of oxygen shows it to have 2 places with unpaired electrons. Since all of the structures we have covered so far have all of their valence electrons paired, it is probably a good idea to use the 2 electrons to pair a couple of unpaired ones. There are several choices as to which electrons to pair, but as long as both extra electrons are not added to this same oxygen, it doesn't really matter. We're going to add 1 electron to each of the oxygens on the left of carbon. Taking one of the extra electrons to the oxygen on top and pairing its unpaired electrons creates a lone pair. Take that second electron and pair it with an unpaired electron on the bottom oxygen on the left. That also creates a lone pair. To remind us that there are 2 extra electrons on these dot diagrams, we will put a -2 in the top right corner. Now we have to figure out a reasonable skeleton for the structure. A look at carbon's dot diagram shows it to have 4 unpaired electrons. There are only 3 oxygens, so at least in the beginning, one of carbon's valence electrons is not going to form a covalent bond. Staying with the convention of building a dot structure, of going left to right and then down, we will hold off forming a bond with the dot on the top. Again, this is just an agreed upon way of forming the structure. 2 of the oxygens look like they are in place to form the skeleton. This one looks like it should move over a bit to get the right orientation. Now, push the dot diagrams together. 3 of the unpaired electrons on the carbon are paired up, forming covalent bonds. Is this structure complete? No, we see that there are 2 unpaired electrons, and they still need to be dealt with. Pushing these electrons into a bonding position is our best bet, and a bonding position between the atoms having the unpaired electrons is our best location. The dot on the carbon is moved into a bonding position between the carbon and the oxygen with the unpaired electron. That unpaired electron is itself moved into a bonding position between the carbon and the oxygen. That leaves us with a reasonable looking structure, and it shows us why carbonate is a -2 ion. It needs 2 extra electrons to form an appropriate dot structure. Do the atoms in this structure fulfill the octet rule? Carbon has 4 valence electrons from the double bond and 4 more from the single bonds. That's a full octet. The oxygen involved in the double bond also counts the 4 double bond electrons, which it adds to the 4 valence electrons it has in lone pairs. Full octet. For the single bonded oxygens, they have 2 electrons from the bond and 6 in lone pairs, also a full octet. This is an appropriate dot structure. It is, however, not the only appropriate dot structure for carbonate. It has resonance because it has a multiple bond and there is a choice of where that bond is placed. In the dot diagram step, when choosing which oxygen to add the extra electrons to, we had picked the oxygen on the right. The double bond would have ended up on a different oxygen. In short, the oxygen that does not get an extra electron will be the one to form the double bond. Any of the three oxygens can be that oxygen and form a different dot structure. Therefore, the dot structure of carbonate will have three structures, including the one we just constructed, and that was not giving the electron to the oxygen on the right. This one comes from not giving an electron to the oxygen on the lower left, and this one to the oxygen on the upper left. Three different structures with the double bond in three different places. From a presentation point of view, parentheses are added around each of the structures to show that the charge belongs to the ion as a whole. Be sure that the charge symbol is placed in the upper right corner just outside the parentheses. Since any one molecule of carbonate can adopt any one of these three structures, include double-headed arrows between all structures to indicate that these structures are related by resonance. Paired dots can be replaced with lines for bonds, as can lone pairs. Carbonate. Recapping the lecture. Atoms with 8 electrons in their outer shell, and that's limited to the s and p orbitals, are the most stable. An atom in a covalent bond gets to count all electrons in that bond toward the fulfillment of the octet rule. Rules for building a dot structure, a basic approach, begin with a molecular formula. From that, we get the dot diagram for each atom. If there is a charge on the molecule, that is handled here. Construct a skeleton with the central atom being the atom with the lowest electronegativity. The arrangement of single unpaired electrons around the central atom is a guide to the skeleton arrangement. The structure is formed by pushing together in overlapping orbitals that contain one electron or dot. Then it's on to the octet rule, where electron pairs are rearranged if necessary. And finally, we look for resonance. Resonance structures only occur when there's a choice of atoms to make the multiple bond. And that completes our lecture. Dot diagrams require practice. Follow the same procedure for every structure.